So we can just get started. Is everyone ready for this?
Yes.
All right, here we go. So this talk, it's more of a conversation than it is a talk. I don't want to just like throw facts at you. We can do that over the internet. This is more of a conversation. I'm going to ask you guys some questions as I discuss these potential features that we could use for this app that we're building, which is a cloud lab for drug discovery. That's what we're going to build here together in 30 lines of Python code. Obviously, this is not my machine, so it's going to be a little bit harder to get Python to compile locally, but we're going to try it anyway. Okay, does that sound fun? Okay. We're going to do this all in Python. We're going to use open source libraries that freely exist on the web. Anybody can do this. And I'm going to show you guys why this topic, drug discovery, which seems so difficult, is actually very doable for anybody, even if you don't have a PhD or a master's or deep domain expertise in any of these biomedical sciences. All right, so let's do this together as programmers, as hackers, as enthusiasts in data science, all right? So the first thing I want to do is say what exactly we're building here. What we are building is a deep learning model that's going to be able to predict the likelihood that some person gets cancer. That's it. We're going to predict the likelihood on a scale of 0 to 100 that a given person is going to get cancer. And the way we're going to do that is, first of all, we're not MDs. We did not spend 18 years from birth till 18 getting birthed, fed, and raised, and then taking 4 years to spend anywhere from 20K to 100K USD on a bachelor's degree, and then anywhere from 100K to 250K on a medical degree, and then 4 years of our lives for residency. So 30 years total, 18 plus 12, 30 years total to be able to make a prediction as to the likelihood of cancer. That's the status quo. That's what normally has to happen. We have to take 12 years of schooling to be able to get the privilege of telling other people you have a 60% likelihood of cancer given your biomedical data that I'm looking at. I am a doctor, trust me. Now, it takes a lot to make a doctor these days, right? 30 years of time and energy and resources that society has to funnel into a human being. What if we could automate that? Just dream with me for a second. What if we could automate that entire, let's say, pipeline? We're talking about a human being here, but a pipeline for an eventual application. What would that look like? And I think I have an idea of what that would look like given a set of emerging exponential technologies that we can all look at on the internet together, namely quantum computing. We're going to go over all of these. Genomics, deep learning, that I just talked about, and last but not least, blockchain. So we're going to go through all four of these together. Blockchain, quantum computing, deep learning, and genomics. All of these are exponential technologies. They're not linear technologies. They double in their output, in their potential every year. So that's what we're going to do. We're going to build a neural network. That's a type of deep learning model, but not just any neural network, a quantum neural network, right? Quantum neural network that generates a prediction of cancer likelihood using genetic data. So everybody is a result of their genetic data. We are genomic beings, right? I've had my genes sequenced. I've talked Sarah's ear off about all my genomics and things that I find interesting about them. But we can predict so many things, thousands of things about you that you would think are vague and very non-describable. We can quantify those things using genomics. And so one thing that we're moving into is an area of genomic drug discovery, where it's not about preventative medicine, it's not about precision medicine, it's about genomic medicine. Medicine where N of 1. The clinical trial is not 10,000 people, it's one person, you. So we're going to make a medicine just for you. It's not going to work for anybody else, but it's going to work really, really, really well just for you. And so how do we do that? Well, we can't just use any type of neural network. We have to use something very special that's never existed before. A quantum neural network that runs on not a GPU or a CPU, a computer processing unit, or a graphics processing unit. We have to use a quantum processing unit, and this is an emerging technology. And lastly, we can't just make any prediction willy-nilly on our laptop, because I can sit here and I can say, okay, Tom, I'm going to take your genetic database, I'm going to feed it into my Python neural network, I'm going to type up 30 lines of Python, and boom, look at my terminal window. It says you have a 30% likelihood of cancer, trust me. That's not going to fly for hospitals. That's not going to fly for real-world applications. We need one more thing. We need something called immutability. That means the ability for this prediction to never be altered. We need a way to trust each other that this prediction that this neural network makes is going to be valid as a doctor would. And that is where blockchain comes into play. Okay, so we're going to go over all these technologies. We're going to use Ethereum for this immutability part. For those of you who don't know, immutability is a very fundamental concept in computer science that means unchangeable. It can never be changed. And instead of in God we trust, we say in mathematics we trust. When it comes to cryptocurrency, that's why cryptocurrencies are not backed by the state, they're backed by the network. They're backed by mathematics and computing power. The other technology we're going to use is just data. Normal data set, publicly available, it's on Kaggle. We're going to go through that together. And the last thing we're going to do is we're going to use this quantum computing library in Python called QI-Skit. It's by IBM, freely available. We can use it on the cloud. It's very simple. We're going to do that together. All right, so that's what we're going to do today. So what we're going to do is we're going to try to automate medicine, right? We're going to try to automate this whole process of trying to predict the likelihood that somebody has cancer. Obviously, there's so many different diseases we could sit here and try to predict, but we're just going to pick cancer because it seems to be, a really bad disease, right? So my first question is, what is something that comes to mind that could be a problem with this idea, this dream of automating the medical pipeline? Does anything come to mind for anybody here? There are no right or wrong answers, just thoughts. We want to start a discussion here. Go ahead.
Public cynicism.
Public cynicism, yes, absolutely. That's a good one. Yes?
We're all way different.
Absolutely. Every single one of us is different. From our thumbprints to our eye scans, we are one out of just infinitely many. So cynicism, we're all different. Any other ones? Yes?
Unknown underlying conditions.
Very true, very true. Like, for example, what would one be?
I'm not too familiar with the medical terminology, but someone could have a heart problem or something along those lines that hasn't been diagnosed or realized.
Absolutely. I mean, what is the number one disease in the United States? Heart disease, cardiovascular disease. That's the number one killer in the United States. So those are all great ones. Underlying medical conditions that nobody knows about. How do we even begin to discover those? Public cynicism and the fact that we are all different. These are all valid answers to this. Does anybody have something else that comes to mind? Sarah?
Medical history, like if you've been exposed to radiation, things you can't typically quantify.
Absolutely. Unquantifiable history. Is that what you were going to say?
Yeah, just the fact that there are certain things that may not show up in genetics, like radiation or future things that may have caused the cancer if they had a low likelihood prior.
That's a great point as well. As somebody who is very much computationally focused, I'd like to think that there's always one source of truth that has all the answers, and it's just very easy and packaged. But you're right, it's more than just genetics. There's the epigenome, right? The disk reader that reads the disk that is the genome that gets scratched over time through what we call the aging process. And so what this is just a variety of medical images, and we can use convolutional networks for image classification. We've already achieved superhuman status in terms of image classification across a wide range of tasks. Radiologists are the first ones that are going to go. My friend Dr. John Billings is a radiologist. We worked on a startup called Sage Health for about 6 to 8 months together, and we're going to deploy this thing to the Mayo Clinic. And so he sent me this data set. I was working on the model for it, and what we found was, even though I could build this really cool deep learning model that could predict the likelihood that somebody had a certain cardiovascular disease, the Mayo Clinic was not going to use this because of the problems that I'm talking about. Because, how can they trust that this model is going to be accurate? How can they know why it's making this decision, looking inside the weights of the model, which are just ones and zeros, and saying, what is the plain English description of why it's making this prediction? We don't know yet. This is an unsolved problem in computer science. So that's the first question that we're going to have to tackle. So how do we build this? So, okay, let's think about how we're going to build this. Well, we're going to build an app that generates different drugs that could very well be a cure or a therapy for cancer for a specific person. We're going to use one person's genetic data, just a single individual. We're going to try to generate a drug for that person, okay? So this is going to be an app, right? It's going to be an app from iOS, Android, and desktop. Just think through this with me, okay? It's going to be an app on their phone, and it's going to use an API, right? Apps use APIs. APIs are essentially basically listeners and microphones to the web. Like, we're saying, okay, here's my genomics data, spit into our phone or whatever it is, a biometric sensor. It's going to send that to the web. It's going to analyze all of that. And it's going to send back a prediction, right? 60% likely that you have cancer. Very simple stuff. But what's the problem with an API backend? What's the problem with having a server that does this? Can anybody answer that question in the pipeline? Security, exactly. If we own the server, we can modify the server. What's to say I'm not going to change the results? I've got a company. I've got investors. I've got to show good results. I gotta build hype for my product. How do we prevent that security failure? And the answer is, we're gonna use an API for sure, but that API is not gonna talk to a server. It's gonna talk to a network called the Ethereum virtual machine. Now, what is that? Let's just go in briefly into what that is. So the first network, the first cryptocurrency was called Bitcoin, right? This was over 10 years old. It's got a market cap bigger than some countries. Today, nation states across the world, England is looking into a digital pound. Russia, China, India just accepted cryptocurrency before it was banned. So let's see, China's 30% of the world, India is another 30% of the world, so that's the majority of the world is now accepting cryptocurrency for the mainstream. This is becoming big here in the United States as well. So this is very much happening very fast. And of all the cryptocurrency networks, Ethereum is the one that all of these states are building their currencies on top of. Why? Because Ethereum allows you to build your own currency that is gas, stable. It's not going to be volatile. Who here has heard of USD coin? Okay, we got one person. I own some USD coin. You got some USD coin? USD coin is great because it's just the US dollar. It's not going to go up. It's not going to go down. One-to-one pegging, right? The great thing about USD coin is I can send my friends in India that USD coin instantly. There's no 2 to 3 day waiting time for wire transfers. And then they can convert it to whatever they need. My friends in, wherever in the world, Europe, wherever in the world. And so if that's what Ethereum does, and how it does this is that Ethereum is essentially a collection of computers. I could set up my computer right now to be an Ethereum node. Tom could do the same thing. And then we become Ethereum nodes. And what we do is we download a database. Ethereum is a giant database. And in this database, it shows every single action that's ever been performed. For example, store data, compute X plus 3. Every single action. So everybody has a copy of this database in the network. I'll have a copy. He'll have a copy if he decides. If you decide, you'll have a copy of it. And if I want to come in and I want to modify something in that database, like let's say a prediction for cancer, every single other computer has to accept that change. But what's preventing them from accepting the change? The answer is a consensus mechanism called proof of work, proof of computational work. What happens is our computers are going to solve randomly generated math problems. They don't mean anything. They're just randomly generated, brute force solutions. But once they solve those problems, it's going to have a solution. And then we put it on the altar of the network and we say, hey, we solved this problem. Here's the mathematical proof. You don't have to trust me. Here's the proof. Look at it. It's right there. And then every single other computer in the network has to accept that change. Right now, Ethereum is mostly used for transactions. Go ahead.
So when you say that the proof is posted, other computers have to verify, or so there are dedicated computers to verify, or no?
There are other computers that have to verify it. You can't just change it. We could change it, but the network's never going to accept it. It's never going to be a part of this blockchain. It's just going to be on my computer. Yeah.
Is this at all related to cryptography and solving huge prime numbers?
Yes. So one example of that is Shor's algorithm. Shor's algorithm is a very famous computer science problem for cryptography. Shor proved that this problem could only be solved using quantum computers, and we're actually going to get into that. So that was a good lead on. Okay, so that's the basic idea of Ethereum. It's a database. Everybody has to download the database, and nobody can change the database. That's the great part of it. Yeah.
How do you solve the chain splits?
That's a great question. That's a great question. So 5 years ago, the chain actually did split. The Ethereum chain split. And what happened was chaos, essentially. There was a lot of chaos. And so Ethereum is a bunch of idealists, right? Bitcoin has been around forever. There's never been a chain split. It is a source of truth.
There's been chain splits.
Not from the main chain on Bitcoin. There have been chain splits in the Lightning Network, but never on the main chain. In Ethereum on the main chain, there was a split. It's because they were trying to get away from proof of work. They were trying to use instead a consensus mechanism for getting the computers to agree called proof of stake. And the problem with proof of stake is it's just not as reliable. Like we know for a fact, proof of work will always work. Yes, it's going to waste the electricity, but it will work. And that was the issue. And so they're still on proof of work. They still have dreams of getting to proof of stake. Not yet. They learned a lot from that process, and they still have the biggest lead in terms of first mover advantage. Many of competing chains, nobody has the developer ecosystem that Ethereum has. So the Ethereum virtual machine, just think of it as a giant computer. It's a computer that exists based on a bunch of computers. So it's like we take all of our computers and we make one massive computer with everything that we would think of in a computer: an operating system, a stack of processes that are happening. And what we're going to do is we're just basically going to use an API to talk to this computer. Just think of it like a server, except it's a server that nobody owns and nobody can change. It's like inscribing our prediction into a stone tablet made of ones and zeros. It's never going to change.
Siraj, is it true that Ethereum's the only blockchain that works on a code base like Selenium, the smart contracts? It's the only one that really does that, right?
It's the one that has it's the easiest to start with that I've seen.
True. But I mean in the sense of you can actually write programs that operate on the blockchain, whereas the other methods of cryptocurrency or cryptology out there are not working at that level.
That's right. That's exactly right. So Tom brings up that point. Bitcoin was created in a way that it is not what's called Turing complete. And in computer science, the term Turing complete means a program that can do anything. Now that sounds very vague, but this was actually for security reasons. For example, with Bitcoin, we can't embed a program in the Bitcoin network that does a simple for loop, something as simple as a for loop. We can do conditionals like if else. We can't do for loops. Why? Because of security. Satoshi knew that this was a bad idea. Ethereum, however, it is Turing complete. We can do a for loop, which means we can generate entire programs. We could make Facebook and put it on Ethereum. People have done this. We can make Airbnb. We can make Uber. In fact, if you were to ask me what the next unicorns are going to be, they're going to be Ubers and Airbnbs, except the users gain equity in the network. Right now, if you're an Uber driver, you don't get equity. You get your measly paycheck contractor. Get out of here. You don't get this respect that you need. But the next wave, as users demand ownership over their data and more equity in the networks they invest their valuable time and energy into, will be using Ethereum and other related cryptocurrencies. The next exponential technology I want to talk about is genomics. And I say it's exponential because compared to 20 years ago, in the year 2000, it cost $100 million to sequence a single genome. In 20 years, now it costs less than $1,000. That is over 100x decrease in price. At the same time, we've seen the number of genome sequenced skyrocket exponentially. And still today. Yes, Sarah.
Yeah.
Oh, yes.
I was going to ask, is Ethereum at all related to the Tor, the functionality of how Tor works?
Yes, absolutely. So Tor is awesome. Tor, for those of you who don't know, is a privacy-centered network. I use Tor. And basically what it does is it's basically a proxy, right? Who here has heard of a proxy? It's a way to, mask your IP address so nobody knows who you are. Tor is a very special proxy in that it takes your IP address and it routes it through every other Tor node in the network. And so there are thousands. And so in order to trace back to you, you don't have to go through one hoop, you have to go through thousands. So it's a very secure network. Does Tor have anything to do with Ethereum? Not really, but there is a specific currency called Monero, which is a completely private currency that is untraceable. Very dangerous, actually. I don't like talking about it that much, but Monero uses similar technology to Tor to allow both the sender and the receiver to be completely anonymous in a mathematically provable way. So, and Ethereum doesn't, but Monero does.
Is Monero Ethereum based?
Monero is very similar to Ethereum, except their focus is on privacy. All of these blockchain networks have some, niche thing that they're trying to focus on. Ethereum is more of a Swiss Army knife. They're trying to do everything. And so genomics, it's getting really, really exciting right now. We still, even with this, we have 0.02% of human genome sequenced today, despite this exponential drop in cost and exponential increase in the number of genomes sequenced. And this is huge because right now, medicine is very much just sticks and stones compared to what it could be, which is genomic precision, tailored to you. Clinical trials take 12 years to get to market. It takes way too long. How can we speed up this process in silico? Forget about in vitro, in silico. All right, now this is the last slide. I'm going to combine two different exponential technologies together, quantum computing and deep learning. So deep learning, right? Neural networks. These models have been around since 1950. Perceptrons. Nothing special. Input times weight, add a bias, activate. Just matrix operations on some data set, and then getting that prediction value, computing the error, and then multiplying that error using derivation, calculus, against those weight matrices in the reverse order to make those weights better. Better meaning more likely to predict the result that you need given some labeled training data set. This is what powers everything that we use today across all the apps we use, Airbnb, Uber, Facebook, Twitter. Everybody uses deep learning for recommendation engines, for self-driving cars, and my Tesla uses convolutional networks to see where it's going. It's literally saving lives in that way. Deep learning came around 8 years ago. It's been skyrocketing in terms of popularity and use in real-world applications. But I am totally disillusioned with deep learning, despite how cool it is, because I don't know about you, but in the past year, I haven't seen a single paper that shows me something super, super cool like I did the past 5 years before that. I mean, I'm happy to be proven wrong. Can anybody tell me a single invention in deep learning, this rapidly growing space, that blew your mind away in the past year?
Well, not the past year, but transformers are pretty darn impressive.
Absolutely. So that's what so transformers were the last thing that I was like, yes. And they were like 2 years ago.
Like almost 4 years ago now with the first encoder decoder. Yeah, that's been a while.
It's been a while. Transformers are very, very cool. That's what powers GPT-3 and all of these state-of-the-art natural language processing models. Yeah.
If you don't mind, what are transformers?
Oh, that's another topic.
Tom loves talking.
Tom's going to talk a lot about transformers.
Well, not tonight, but another time I can.
He has a video that's on my YouTube page that you can look at. It's
Just
very accessible.
nothing impressive, just how to get started with them.
I mean, they can do everything. I mean, in terms of natural language processing, whatever you want to do, they're very impressive. The ones that have been trained by Google and by Facebook and by the OpenAI, the giants on Reddit data. Because if you think about Reddit, it's publicly available. Anybody can look at Reddit. And it's structured in a very unique way because of the upvote system, right? The upvote system percolates the best answers to the top. What does best mean? Best is democratically decided by the users of Reddit. But generally, the top comment is pretty accurate, right, for Reddit. And so that's why it's so good. It's not because it's some kind of, great, AI machine that's ambiguous and we can't really figure out why. No, it's because the data set is so wonderfully structured. But still, it's really good at text classification and generation and chatbots and all sorts of applications, sentiment analysis. And so, yeah, they're state-of-the-art in NLP.
Is this what's under the hood and like curated ads on social media and that sort of thing?
Yes, it is, mostly deep learning. We have the greatest minds on the planet working on gluing our eyeballs to these ad networks, which is why I don't use Facebook or any of these social networks, TikTok. Even though I have a YouTube channel, I don't sit there and look at the newsfeed. I think it's really dangerous for us and our progeny to be looking at these networks that are influencing us in ways that we don't even understand, that they are smarter than us in ways that we don't understand. We're flawed humans. We're not as good as these networks that are trained on thousands of data points about ourselves. Eventually, these networks are going to know us better than our spouse does. They might already, actually. So it's very scary in that way.
That's it. The Social Dilemma. Is that
The Social? That's a great movie. Okay. The Social. I love that. So that's deep learning. The quantum part is saying, how can we improve these models in a way that has never been done before? Quantum computing, the cliche thing that everybody says is that for a bit, it's either a 1 or a 0, and then for a qubit, it's 1 and 0 at the same time, right? Another way of looking at that is the coin flip problem, right? So if I just sit here and flip a coin, we can say, okay, it's going to be 50-50. It's going to be 50% likelihood that it's head, 50% probability that it's tails. But if we miniaturize myself and the coin down to, hundreds of thousands of x to the quantum scale, and I do the same problem, we cannot use probability theory anymore. Probability theory does not apply. We can't even use the word probability to describe this coin flip. We have to use a different word entirely called amplitude. And amplitude is probability at the quantum scale. And amplitude is really weird because we can have several different amplitudes for an event like that, like a coin flip, but those amplitudes don't have to percent equal 100%. They could be over 100%. They could be a 200% likelihood total amplitude. There could be a 50% likelihood of heads and tails, and then an 80% likelihood of tails. And that doesn't make sense to us because when we think of things very binary, but the world is a light show illusion. And at the quantum scale, things happen that just don't occur in our real world, and we are just not meant to think about these things in that way because we're not that small at these very small scales. But what we can use from those small scales is this tool set called quantum mechanics, namely what's called the wave function. And what the wave function allows us to do is perform mathematics not just on real numbers like 1 through 9, but on a different set of numbers called imaginary numbers. So I'm going to ask a very probably basic question here. What is the square root of 4? Can anybody answer that? Sarah says 2. You say 2. Yes, exactly. Now, exactly, the square root of 4 is 2 because it's 2 times 2. Now, here's a little bit harder question. What is the square root of negative 4? Yes. All right, thank you for that. Good. No, good. Extra points. What is the square root of negative 4? 2i, exactly. For those of you who took Calc 2, I think it was. 2i, because we can't just take 2 times 2 and make it equal to negative 4. We got to add something in there that doesn't exist in the world that we see, an imaginary number. So if we take 2 times this imaginary number I, and we multiply it by itself, if we square it, then magically, imaginarily, it's going to equal negative 4. Now, those are the types of numbers that we have to use at the quantum scale to compute anything, because amplitudes aren't just a miniature probability, they're a possibility space that doesn't exist in our reality. Now, what else is a possibility space? Deep learning, deep neural networks are a possibility space of predictions. Usually, they're predictions on a scale of 0 to 100%. What's the likelihood that this is a dog versus a cat? But if we could use the mathematics of quantum mechanics inside of a deep neural network on normal classical data, we might be able to create predictions that are much better than we could have otherwise, especially on genetics data, which is incredibly complex. Forget about thousands of features, tens of thousands of features. And so I think that quantum deep learning is the next stage of deep learning. We're going to start using quantum computers and quantum mechanics, the math, and the hardware of quantum computing to be able to make better predictions. And the great thing about quantum computing theory, it's a whole different theory from deep learning, is that if we look at this is actually what's called a variational circuit. What this is essentially a graph of matrix operations, matrix multiplications. And all of these boxes are called gates, quantum gates. And inside of these gates are just, again, matrix multiplications between different variables. But these variables aren't just ones and zeros, or else it would be a neural network, because if you look at it, it kind of looks like a set of layers, right? Input times layer, times layer, times layer, times layer, times layer, output. The difference is that unlike this deep neural network where the layers are essentially real numbers, these involve imaginary numbers. So we cannot use linear algebra like we would normally. We have to use a different tool set that uses linear algebra, but on quantum, but also using quantum mechanics. And yeah.
So will this come up, will you end up with different outcomes, or will you end up with the same outcome faster? Because it can calculate it all at the same time.
Yes, exactly. So it's going to do both. We're going to get different outcomes, and then we have to use what's called a classical model to choose the best outcome. And then the hope is that overall that will be faster. But that's still TBD, right? Google did prove quantum supremacy 2 years ago on a very small toy problem. Quantum supremacy is the idea that a quantum computer could do something better than a classical computer. Google proved that mathematically 2 years ago. The question is, can we then use that for deep learning? That is an open question, but I think it's a very exciting question.
It is an open question.
It is an open question. Absolutely.
Absolutely. How can, I guess this might be too long a question to answer, so if it is, about it.
No, go for it.
How can imaginary numbers that aren't real be used to predict real things?
That's a good question. So just think about the input data as being a bunch of strings and numbers, whatever, images, videos, right? But essentially, we have to compress that data. We have to parse that data into just numbers, right? Just to make a giant matrix, pandas data frame, let's say. And that, obviously, it could be too big to fit in memory, but we could fit it into a CSV file, whatever it is. Essentially, we're going to convert it into some sort of regularized, giant collection of numbers. Those numbers are not going to be imaginary. Of course not. But what is going to be imaginary are when we apply these specific set of operations, like the wave function, to those real numbers. That's going to result in imaginary numbers. Now, the wave function, essentially one way of saying that when I don't look at something, it's going to be in a possibility space. But when I do, the wave function collapses and something is picked. But it doesn't have to be just a human. It could be any sort of mechanical observer, an instrument of some kind, a magnifying glass, anything.
I could be entirely wrong. This is a kind of like Schrodinger's cat.
That's exactly right. That's where it comes from, Schrodinger's cat. That was
the probability field when you're looking at like where electrons would be. You don't know where they're going to be. You know approximately where. You don't know exactly look.
exactly. So very useful for predicting the likelihood that a cat is alive or dead, but also very useful in predicting many things. Like we wouldn't even have this computer without quantum mechanics and Schrodinger's cat, because we had to use quantum mechanics to build the transistor and the motherboard. Like electromagnetism required us to use quantum mechanics to build those things. So very useful in real hardware. Also, it's going to be useful in quantum computing, I'm sure of it, and quantum deep learning is next. Lastly, I didn't explain this thing. This is basically just an animation which shows a possibility space of zeros and ones. Normally, it's going to be binary. In this space, it's going to be all of them at the same time. So we're just going to get a plethora of possibilities, and it's our job to decide how to optimally pick the best one. Think of it like an output array, 1D array of classifications for an image, except they're going to be probability values, not probability values, amplitudes. Okay, so those are, go ahead.
Real quick, based on your very honest presentation, I hear you saying this isn't even in its infancy. It's waiting to be born, but we hope it'll be born soon.
We hope. Exactly.
Okay.
Exactly. And it's going to require the intersection of 4 different exponential technologies: quantum computing, deep learning, genomics, and blockchain, all of which are happening today, right now. Okay.
Siraj, what is necessitating quantum? Why couldn't we use classical computing for this? Is it just not fast enough?
It's a question of speed, right? I mean, drug discovery takes 12 years. It is a very, very difficult problem, and combinatorial explosion when you take into account thousands of people's genes and all the related data. It's just too much data.
It's not just diagnosis, it's also prescription. It's the whole pipeline of that process.
Prognosis, diagnosis, all of it. And gene therapies right now are just made, they're called gene therapies. They're made for people with diseases that nobody else would have. A really terrible disease like cancer for a kid who's 3 and they're going to die, or something that's really it's only for them. But eventually, I think all of us are going to have gene therapies tailored for us, or at least our children.
The cost of quantum computing, though, is probably a prohibitor into that space, though. But even though sequencing is less expensive, quantum computing is not. And I know it was used to help with COVID sequencing and the vaccine. HPV donated a quantum computer for help with that. So
I'm wondering if the answer is if one quantum computer was shared by the world for this, it could do the job for the world.
Absolutely. It could.
So it becomes, if the world shares the cost, it's not as cost prohibitive, correct?
Correct. Yeah.
So I think I am making updates, but I believe quantum computational theory can be done on equipment we have represented in the West, which can be enforced in an actual quantum computer, and only a couple in the United States. So you can still achieve what you're trying to work out using physics models and such.
Exactly. You're exactly right. Yes, it's super expensive. Absolutely, that is a problem. And how do we prevent just the giants from having access to it, like Google and IBM? How do we put it in the hands of people? They themselves are trying to create cloud APIs. We're about to use one so that anybody can use it. But how do we get it to be cheaper? I would just defer to the argument of economies of scale and how phones were expensive and genomics were expensive, but these things are going to, we'll get there. And let's start coding before, how much time do I have left? 5 minutes?
I mean, we don't really have a limit.
Okay. Real quick, last math.
That's what we do.
Okay, perfect. Last math thing before we get into the code here. 30 lines Python code. I just want to say that look at this box. This box represents a machine, and this machine has n different states, right? It can be red, blue, green, orange. And we can represent all those states as a set of numbers, 0, 1, 2, all the way up to n, right? Where n is the number of states. Very simple stuff. Now, what's another way of for us to represent these set of states? Well, we're going to use vector notation. We love vector notation, right? So what we can say is that this vector is going to equal all of those possible states, where those states are across all real numbers. And that is what we normally do, right? This is basically the format that class probabilities come out in, right? Class predictions for image classifiers. They look like this set of arrays that are across all the tutorials on the web. But what we're going to do is we're going to take that up one step further, and instead of just class probabilities, we're going to use that same vector notation, not to quantify states or probabilities. We're going to use it to quantify amplitudes, because we're going to be using a quantum computer in a second to do so. And when we do that, we can represent it as this sigma notation, which says the vector is going to be equal to all of those amplitudes, not probabilities, summed up together, including imaginary numbers, not just real numbers, imaginary numbers. So this is not my machine, but we're going to try this anyway. All right, so we're going to go to Colab.
So run the code on the laptop.
Actually, I think a Google Circle will be running your code, right?
Yeah, I mean, if I can get Sparklight to leave me alone, there we go. Let's just start going here. And we're going to make it big so everybody can see. Let's see, cancer solver. Let's just be really bold about this. Okay. So what's step one? Our first step is to import our data sets. Okay, what are, or not just our data sets, but our libraries. What are the tools that we're going to be using here? Let's see. We're going to import, well, we need our data, so we're going to import the Kaggle library to import our data set. We're going to need to import JSON for parsing. We're going to need to be able to parse whatever our data is. We're going to need to import requests to talk to Ethereum, right? We need a way to talk to the web, to the Ethereum node. And lastly, we're going to import our quantum library to do quantum computation. And so the way we're going to do that is we're going to say import qskit. Okay, and so that's that. We are going to just keep going here. Okay, so now let's get to step one. Let's also write step two, and let's also write step 3 and 4, and that's it. We have 4 steps here. It's a 4-step process. We'll keep it real simple because we only got 30 lines of code. We cannot write more to incorporate these 4 exponential technologies. Okay, so step 1 is going to be to initialize our blockchain. And that blockchain is going to be which one? Does anybody remember? Ethereum, correct. Good job. So that's going to be Ethereum. Our next step is going to be to prepare our data set. This is going to be a genomics data set. Very exciting stuff, genomics data sets. Exponentially more available to us every single day as the millions of people across the world get their gene sequenced. And the last step will be to generate what's called a quantum neural network. We're going to generate a network. We're not just going to write a network. We're going to write a program that generates these networks for us. Oh, and there's one more step, actually, I forgot. There's going to be, the last step is going to be to retrieve the response, right? We're going to initialize our blockchain, prepare our data set, generate a quantum network, make a prediction using that, and then we're going to retrieve all of that from the web, and the web in this case is Ethereum, the network, the entire network. Okay, so let's now write out what this looks like. Retrieve response. Okay, so the first step is for us to say, okay, our session is going to be initialized using the requests library. Let me make this much bigger. Okay.
Not yet.
No, it's not running. This is a demonstration. I swear to God, it's running on my laptop. And anybody who wants to see it run on my laptop, come talk to me afterwards. I've got my terminal window open. I was so ready for this. It is here. Okay. It is generated. You guys can't see it back there, but when you come up here, I'm going to show you this thing, which generates, boom, you see that? It generates these quantum neural networks in real time. Come to me after, I'm going to show you. Right now, I'm going to write it out. So think of this as pseudocode, because I'm not about to install Kaggle's API with the authentication and QI-skit. It's kind of a pain to do so on a new laptop. I don't want to you know what I mean? So let's just keep going here. So request.session, we're going to initialize a session, and the URL is going to be what's called Ropstein. So what Ropstein is it's a network. It's basically a normal server like any other server, but this server talks to the Ethereum blockchain. And so we're going to have some kind of key phrase here, key phrase, whatever it is. And this URL basically lets us use the request library, which is essentially just made for server-client communication, very basic stuff. We don't need to do anything fancy like smart contracts. We can just talk to the server, but the server has the logic of talking to the Ethereum nodes and putting that immutable data on the Ethereum network. And so that's that. Just two simple lines for this first step. Initialize our blockchain. Now the next step is going to be to prepare our data set. So let's see if we can find this data set. We'll search genomics, Kaggle, and let's see if we can learn a little bit about what data set we have. It's called the histones. We're using histones to predict the likelihood of, is this not Google? What is this? Okay, going straight to Google, not that. Okay. What, sir?
It's a Quorum. I don't remember which one it is.
Just kidding.
No.
I use Big, of course.
Nice. So what this is a data set from a competition, and for 5 different genes, it shows 100 different factors on a scale of 0 to 1 that are related to a topic called histones. Histones are one of many different genetic markers that a single gene will have. Let's take a look at what this data looks like. Please tell me we can see a little hint of it. And okay, I'm not gonna do this. That's fine. This is genetics data, freely available on Kaggle. You just have to log in. Okay, and basically it's 5 different columns with 100 rows each. Each of those rows for those 5 genes, X3, X9. Each gene has a different label of 5 different alphanumeric characters, and it's got 100 different rows. So 5 different genes. Each of them, and they all have thousands of genes, but those 5 genes each have 100 rows, and all 100 of those rows describe a different pattern for what are called histones, one of many features of those genes. And what we can do with that data set is we can predict how these genes are expressed using those histones, and then ultimately, if we can predict how a gene is expressed, we can predict the likelihood of a given cancer. Now, that seems like a kind of convoluted process, but high level, that's what's happening. To not get into too much biomedical domain knowledge detail, which we don't even necessarily have to do. Ideally, we just give a machine this very complex data that we humans don't understand, and it will learn what's the best thing. It will give us plain English descriptions of what the best parts of it are, what the most relevant parts of it are for the question that we're trying to answer. So we'll use the Kaggle API to pull that data directly from Kaggle. We're going to have to authenticate, which I don't feel like doing right now. And once we authenticate, we'll get the data set, and the Kaggle API will give us that data set. And we're going to have to say what that name of that data set will look like. It's going to be called like genome. It's called like gene expression prediction. Okay. And that's that. So that we have the data set. Let's get to step 3, this quantum neural network. And the quantum neural network is going to give us back a network. So it's going to be let's say it's going to give us back a neural network because we want to generate one. We're not going to write one. We're not going to say layer 1, layer 2, layer 3, layer 4. We're going to have it generated for us. Okay, so this thing's going to generate a neural network for us. It's also going to give us a prediction from whatever it generates. And that function is going to be called generate network supremacy. So quantum supremacy is going to generate that given the data set. So we're going to give this thing our data set, and then somehow it's going to say, here's the ideal prediction for the gene that is most likely to predict cancer. And here's a neural network that you generated. This quantum, let's call it quantum neural network because that's what it actually is. It's basically going to generate a jumble of imaginary numbers and real numbers. It's just like neural networks are jumbles of linear algebra. Quantum neural networks are jumbles of Hilbert algebra. That's what it's called. It's called Hilbert algebra. It's basically linear algebra, but when you're applying it not just to real numbers, but real and imaginary numbers. And our last step here is to just say, okay, once we have that, let's print it out. And we'll print it out. We'll see what it looks like. We'll see what the prediction looks like. We'll make sure that it's nice and pretty for us. And the last step for us is to say, what are we now going to send to the server? What I want to send to the server as data, and this is why we imported JSON RPCs, because Ethereum, the Ethereum network, is going to ask us, well, guys, what are you actually sending to the network? Are you sending just a transaction? Are you sending data? Are you sending the model? What are you sending? And so we have to actually pay a little bit of ether. It's called gas. It's called ether. Another word for it is gas, to be able to store that forever on the Ethereum network. You gotta offer something. You can't just expect them to do it for free. Store data forever. That's a huge task, right? We pay AWS every month to do this. So we're going to give an initial gas price to the network to store something. Let's just say it's one, whatever that is. And the last step for us is to say, well, what are we actually giving to the network? And what we're going to give to the network are a set of parameters, which are the quantum neural network itself, the prediction, and the data set. We're going to put all three of those things on this, and we're going to say the ID of this is going to be 1337. We're going to give it a unique ID, and we'll close it out. So what we're doing is locally, we're generating a quantum neural network using this magic function here that we haven't even talked about yet. And it's going to give us a network. It's going to give us a prediction. We've got the data set. And we're not just going to put one thing. We're going to put all three things on the network. So on the Ethereum network, we're going to take this data variable, which is encoded in JSON, all three of those things, and we're just going to put it on the Ethereum blockchain. So the data set that we use for our experiment, the model that we use for our experiment, and the output prediction that we're claiming in our amazing paper that you have to trust us on, all of that is on the Ethereum blockchain, and no one can ever change it. And everybody gets to view it from afar. That's pretty cool.
Is this for one diagnosis and prescription or for many?
This is for one specific diagnosis and prescription for one person. Keep it as simple as possible. But ideally, we can generalize it. Make it. Ideally, it's not even that we generalize it. We get drug discovery down to a point where we can do it in 30 seconds. You'll just come in, give me a blood sample, and I'll be like, type it into my computer. Here's your pill, right? Bye.
Now, real quick, you're generating a quantum neural network, but you told us we can't do that yet. Is it on a quantum simulator?
I mean, that's exactly.
Sorry.
Yes, that's the next step. Yes.
Okay.
So let's talk about how we actually did this, how we're actually generating the quantum neural network. And it's using this QI-skit library. And so I keep imagining, don't be sorry. Who needs Google? Pick something else. I like it. So, obviously, we don't have access to a quantum computer here. We have this classical laptop. It's a wonderful laptop, but it doesn't happen to have a QPU on it. So what we're going to have to do is we're going to have to use an API that has a QPU on it and just normally talk to it like we would with any other server-client architecture, except we don't even have to do that. We can simulate what it would look like, but on this machine.
Sorry, I'm going to ask you a very maybe a tricky question, but what allows it to be stored forever is because it's distributed? Is that true?
It's stored forever because it cannot be changed. What would have to happen for it not to be stored forever is for someone to take over the network. And in order to take over the network, you would have to have a computer so big that nobody has a computer like that. For the Bitcoin network, for example, you would have to have more computing power than the 500 fastest supercomputers in the world combined. And that was actually 10 years ago. Now it's probably like 1,000 fastest supercomputers in the world combined. So let's say if Russia, China, the United States, and just every country combined and pooled all of their computing power together and said, we're going to destroy Bitcoin. They still couldn't destroy Bitcoin. I believe that Bitcoin will outlive me, my children, all of us. Bitcoin is more powerful. It will survive a thermonuclear war. It is indestructible. It is the source of truth. And Ethereum isn't quite there in terms of Bitcoin, but it is the second biggest crypto in terms of market cap. Definitely more interesting applications are on it.
Theoretically, sorry.
I'm just asking, like, physically, all of this data is stored and some people are volunteering to be on this
the network guarantee or make sure that there's always enough volunteers to keep this data stored forever?
The network doesn't do that. It doesn't keep track of that. We just assume that people are going to do that because there's money involved. There's a financial incentive to do so. Miners in the Ethereum network get paid to do so.
Yeah, I was just gonna mention like back in the day, I used to mine Bitcoin, like 5 or 6 a day, and I had GPUs just sitting there crunching on numbers, tons of data, and those types of rigs are the rigs that are making sure that all that data is accurate.
Yes. Very cool. Very cool.
Yeah.
There's also like full farms that are like the size of this building in China that are just full of GPUs that are just cranking away constantly. They're making lots of money.
Yeah, but like I just read this article recently where China just like went to a place that owns like a big farm and they just abandoned it. They told them all to like go home.
So with Bitcoin specifically, it's like the transactions are the blockchain, and after like 10 transactions, it's unfeasible to change any of it. I imagine this is similar, where after a certain amount of time, it's cemented in that this is going to endure because of how difficult the computational power is to change it.
How is the data federated?
Question.
That's your question.
That's a good question. No, that's the right question. There's a technology called sharding. And sharding, that these days, it's been called sharding. These days, it's now called ZK rollups. This is like some advanced crypto stuff, really cool stuff. But Ethereum is on the forefront of this. Vitalik talks about this a lot. The idea is that your data, when it's stored on a computer, it's actually split into many different pieces, shards, and then all those shards are encrypted in different ways. And then the decryption scheme is specific to those specific shards in a specific time period. And this is called sharding, and then ZK rollups is basically a specific sharding scheme that allows us to do this really fast. Because one of the problems with Ethereum is very high throughput, and the network is facing a lot of congestion. And this is just like a huge problem right now. But a lot of different solutions, it's very exciting stuff. Just look up like congestion Ethereum for a related answer to that.
So this is just a question for everybody, I guess, but like Bitcoin alone is already for a nation probably the 6th highest usage or 8th highest usage or something of electricity, right?
Yeah.
So is it reasonable for us to put so much data onto an Ethereum network, like at a social level, just to prove that we were right when it said you might have a 60% chance of being?
It's a great question. I mean, that is the biggest criticism of Bitcoin. It is valid, the fact that there are miners today that are buying power plants just for mining. Like, it's at that level. Without a doubt, Bitcoin is consuming more electricity than some very small cities. But I think that one of the immutable concepts of humanity, and this kind of goes into philosophy, and I want to hear other people's thought about that, is greed. Like, as long as we've been alive, humans have been greedy. If there is a shortcut, there will be someone who takes that shortcut if it exploits other people. There will always be people who exploit other people, not just empower other people. And how do we counteract against that very innate human bias? We need something that is just crazy expensive computationally, apparently. I mean, there are so many brilliant people in cryptocurrency that are looking into ways of creating a network that is as secure as Bitcoin without that computational, expensive proof of work algorithm. Nobody has come close. Ethereum is still dreaming of doing proof of stake instead of proof of work. How long has it been? They still haven't converted. The network split even when they tried to. So as bad as proof of work is, it is the best solution we have for not having to trust bad actors on the internet that we don't know. But yeah, it's a huge problem. I hope it's solved. I hope it's solved. Yeah.
Haven't historically we've seen those bad actors, like the Roaring Twenties, for example, tends to not benefit the masses, whereas in the case of Bitcoin, it's something that the masses are almost, we do use, but we don't reap the benefits of those people that have the ability to buy power plants and mine ridiculous amounts of Bitcoin. Like, sorry, I'm struggling to articulate myself well here. What's the reason that it can't be distributed to everyone rather than this one actor who we're just going to trust is going to do the right thing.
Well, the network is not stored on any one computer. It's stored on everybody's computer, and everybody has an equal shot of being a miner, being a validator, being a user.
That requires a lot of capital.
It would require a lot of capital if they switched to what's called proof of stake. So instead of proving your computing power, right now it requires a lot of computing power, you have to prove you have a lot of coins, a lot of stake in the network. And so one of the cons of proof of stake is that the richest people are going to be the ones who are proving those transactions are valid. Right now, it's the people with the most computing power. And apparently that's more democratized because people with a lot of computing power aren't necessarily bad actors, and even if they were, they couldn't do anything about it because there's always a bigger fish, a bigger computer. Whereas if it was just proof of stake, I don't know, it just, as bad as proof of work is computationally, it's still the only thing that works. You know, it's been around so long, and it's going to continue to be around.
I don't know if it's always been like this. Is a valid argument for continuing to keep things the way they are.
You're absolutely right. You know, there are smart people who have the opposite opinion. And they're like, Bitcoin was just the first. It just showed us the way. We are now going to build the future, Ethereum, other things, other consensus mechanisms. Forget proof of work, you know? And that's totally valid. I will be happy to see it when I do. I just haven't seen it, you know? I wrote a book called Decentralized Applications 5 years ago for O'Reilly. And I was in India, and I was in Japan. I was traveling for 6 months, looking at a lot of the issues in terms of not being able to transact in the way that we do in the West, or not being able to trust one another in the way that a lot of more developed countries can. Looking at how technology could help solve those problems. And you know, this was in 2014, very optimistic about this stuff. It's quite a while, a bit longer than that. It's been a while since then. But I feel like now it's all that stuff starting to happen. I thought it would happen back then. Now it's starting to happen. And we still haven't found anything better than proof of work. But I'm sure we will. It's just a matter of time.
I'd love to talk to you about this.
We'll talk about it, all right? And I'm pretty much out of time, I think. But let me just say that, one last thing, that went over a million points. Let's just write out this last line here. We're going to retrieve our response using that session that we created earlier. We're going to make a post request to that URL. We're going to give the JSON the data that it needs that's encoded there. And lastly, we'll retrieve the response. If the response is okay, then we'll print out that response. Else, it's a failure. All right, we won't even write the else. Just if the response is okay. So just to recap here, we initialized the blockchain, the Ethereum one. We prepared our genomics data set. We generated this quantum circuit, this quantum neural network using this function from QISkit, just a very basic, simple helper script. And then we put the model, the data, and the prediction all on that blockchain. Nobody has to trust us with our paper. We can have a more trustful system between everybody. It's much easier for all of us to trust each other with this. And if you want to learn more about quantum computing, I think QISkit is probably the best way to do so. It's definitely got the most documentation for me that I like to read. And the way that this network was generated was using a set of seed operations and then just applying random variables to them through matrix multiplication. And then bada bing, bada boom, there's a quantum neural network. Very basic stuff. It could be much more complex. It is much more complex. But I just want to give you a little taste of all these technologies and how they could play together nicely, and how it doesn't just have to be Google and Facebook and Apple and developers there that are developing the coolest stuff. We independent developers can do the same. It's still possible. We just have to use technologies that are thinking a little bit outside of the box. And with the internet, with the web, we can all learn these things. We don't have to get into these very long programs, institutional organizations. We can do it independently with the internet. I make most of my money from the internet, more than my day job. I work at a company called Athena, and we make vaccine passports. I'm the chief data educator there. And I work with Dr. Siddharth, he wrote this book called The Gene. I'm very excited to be working with him on this stuff. So I'm learning a lot about that, but still I'm making more from the internet. And so that's, all that is to say that the internet is going to supersede nation states. You know, the Leviathan was always the nation state, but now it's the network. And we're seeing that with cryptocurrency. We're seeing that with these technologies like deep learning that are automating jobs that we thought were going to be, stuck in place, immutable, like even being a doctor. We can automate large parts of that. Genomics data is changing medicine forever, and blockchain is changing how we as organizations structure and coordinate amongst one another. All of it is based on the internet and the network. Last question.
I'll save it for later.
Okay.
I have one last one. It's petty compared to that wonderful closing. This GitHub, is it just quantum simulation? Well, I don't mean just, but it's simulating quantum computing rather than using an actual quantum.
Totally simulating quantum computing. And so that means that the results are not going to be as accurate. Because, how could you truly simulate the amplitude, right? If you're not using the actual wave function, but it's an approximation. And it's just useful for testing. All right, go ahead.
So I'm not terribly familiar with Ethereum or the network or any of that sort of stuff, but it kind of sounds, if it does have a public ledger system and people are putting their genetic information into that, wouldn't that worry a lot of people with having their genetic information on a public ledger?
Yes, it would. Which means we would have to encrypt it first. We'd have to encrypt it client side before we send it to the network, and then only we get the private key. And what it looks like to them is just a bunch of jumbled up numbers. And we didn't do that, but good catching that.
I want to go back to David's question, and because I don't understand some of that, I have a sort of a slightly different perspective. So can you actually, assuming that this solves cancer, can you actually understand how much embedded energy, how much embedded CO2 emissions is in the solution so that you can contrast it and look at the trade-offs between whatever would be the sort of the long-term impact for the planet when it comes to questions of the Anthropocene, for example, versus solving cancer? Is that a calculation that you can actually make?
I think so. I was invited to CERN. Are you familiar with CERN?
Yeah.
CERN, super cool. I was super excited to be there. You know, just remembering all of these scientists who spent their lives studying biology and physics and climate science and all of these things. And basically what they were doing was they were looking at data sets and they were using their domain knowledge, what they learned, to pick the most relevant features for the prediction that they were trying to make, right? We could automate that. Deep neural networks decide what the best features are going to be, assuming that we're asking the right questions and we have the right data. So I think that large parts of science can be automated. It can be much easier, and developers who don't have PhDs can also do this stuff very easily. They can today. I think it's going to get easier and easier. I'm very excited about climate science stuff too, so I think that's really cool that you mentioned that. Okay, everybody. Thank you.